I think that something is going on here, right, Radek?
Yeah. Everything is recording, I see.
The recording has started. Okay,
Yes,
so
yes.
yeah. So uh, let's keep it professional from now. So
Yeah.
what we have here today is CFD post-processing webinar. What do we do is everything like usual, right, Radek?
I hope
It's
so. I hope
on
so.
my clock. It's 1 minute to 2
Hmm.
p.m. So hopefully we start on time. And let's see. I'll take a look. We already have a couple of attendees here. Yes. Okay. So again, I will start with general introduction and everything, and I will when I'll run out of my ideas and energy and everything, I will switch it over to you, and you will just show
What
the
I
real
can.
stuff.
Yeah,
Yeah. Okay. Okay.
sure. And maybe anytime the attendees can ask, right, for specific visualization, for
Yes.
example,
Before we
if
start,
they have
I'll try
limited
my best
time.
to say it again, but
Okay.
this should be as collaborative and open as possible because the CFD post-processing is a huge topic. We realized it this morning when we started to make preparations for the webinar, and it's a huge topic. There are a lot of details and everything, and it's difficult to cover it in the whole concept. So everyone should be asking questions, and we'll be happy for that. So we'll take it quite easy today. Um, so what's on my clock? It's 1 minute over, so we'll start the webinar. Okay, so I need to switch. Yes, switch it here. So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you our knowledge and our experience with CFD post-processing. Today's webinar is part of the series of webinars. So we 2 webinars back we had CFD pre-processing webinar, and then we had the next one which was connected, which was called CFD simulation setup. And today's webinar is continuing the process and the workflow, and so it's called CFD post processing. So welcome everyone. Make yourself comfortable and think about what you need in your projects and tell us, and we'll be happy to answer. So today's webinar will be hopefully uh, dedicated to your questions and our answers. So we are happy to answer your questions, and we'll do our best to show everything what we know about, or how we do, or how we feel, how we understand uh, the philosophy of CFD post processing. Uh, the webinar is being recorded, and the recording will be later made publicly available to anyone on our YouTube channel. So feel free to hang on. And what else? Together with me on the line is my colleague Radek Maca. So let's check the connection works. Hello, Radek. Can you hear us? Can you see us?
Yes. Hello, Luboš, and hello, the audience. I can see you. I can see the presentation. I can hear you. So I think everything goes well.
Okay, thank you.
Yeah.
So I think we can start. So hopefully we have everything covered. So I would like to ask the audience to make it easier for us. Ask your questions. Ask simple questions. How did you create this image? How did you create that? Really ask about anything, and we will do our best. Uh, okay. So as mentioned, uh, sorry, I guess we will switch the cameras off like usual, Radek, right?
Yeah, sure.
Yeah, because it gives, I believe, better aspect ratio of the screen. Okay, so as mentioned, we created this webinar series. So the first webinar was about CFD about CFD pre-processing. So we recommend it. It's on our YouTube channel. The next webinar was CFD simulation setup, and today's webinar is this CFD post-processing. So we will continue with what we are explaining in the whole workflow. So it can also serve as a education materials for those who start with TCAE or OpenFOAM or these open source workflows. So it's definitely recommended. The agenda of today's webinar is this. I will start with the necessary introduction, but I promise I will be short. Then we will continue with general thoughts about what we think about post-processing, and then we can also discuss principles and general thoughts, and then we have a couple of examples where we can discuss typical examples and typical way of work and typical workflow points. And at the end, there will be Q&A session dedicated to your questions and our answers. So feel free to ask your questions. All the questions will be answered. The most representative questions will be answered right away in the webinar. And I would say specific questions will be answered later via email, but you can be sure that all the questions will be answered. So I think, yes, we can go ahead. So very quickly, CFD Support is a company located in Prague, Czech Republic, 15 years on the market, hundreds of industrial projects delivered, and we are currently creating software which is actually it's already on the market. So we are developing software called TCAE, which is in fact a comprehensive simulation environment where the users can use open source, OpenFOAM, and other open source pieces to run engineering simulations. TCAE consists of software modules. They're independent and they can be used in individual work schemes. It depends on every engineer and on every business and user how to use the workflow. It's extremely flexible, it's extremely automated, and we believe it's ready for industrial projects. The beauty of TCAE is there are no limitations on number of users, jobs, or cores. It's really unlimited in every way for just one single license for every business or for every unit. And there's a wide range of licensing and collaboration options as well. It's based on open source. It means that it's built up on open source, which is a huge benefit because here at CFD Support we have mastered the ability to integrate open source pieces and turn them into professional software for the industry. That's definitely a big benefit. So we are quite small company that know how to use open source and develop on top of open source, which is big benefit because we do not need to develop every detail from of every piece of software, but really we built what is successful already and we make it even more successful. So that's a huge added value. Our software is focused, it's accurate, and it's automated. And it's available for a really wide range of using options. So it can be used remotely or, of course, locally. It can be used on laptops, desktops, clusters, clouds. It can be used remotely from home or from the office or in the office. It can be used natively in Windows or in Linux, in batch mode, in graphical interface. The workflow is very consistent and well tested. So we believe there are a lot of usage options for everyone. It's been tested many times. There are 15 public benchmarks that are transparent and repeatable anytime. There are more than 50 tutorials, which are, again, of course, available, and we have quite good technical support to make sure that everything works smoothly. Current stable release is 25.3. We are, of course, working on new versions. For the future, we will definitely focus more and more on optimization, which we believe is a big trend and paradigm shift in the on the market and in the industry. And also we are developing our acoustics module. We believe it's a big, quite big deal and unique capability of our software. And for the future, we are definitely developing a new software module which is called T-Base, and it's going to store all the data about your simulations and about your product and help you to make smart decisions using surrogate models very quickly. Okay. So these are our future developments. So we are excited of all of it, what's happening out there and in here. And I would start with my general thoughts or our general thoughts about post-processing. Radek, I would like to ask you to interrupt me anytime if I say something what you would like to complete with your thoughts. You are very welcome. So I'll go with the post-processing is extremely important stuff, right? Because you are turning the numbers into valuable insights, right? So it's extremely important because I would say it's a final step of large expensive workflows of large process, right? So you do all the stuff from geometry creation, cleaning, meshing, and then setting the simulation, running the simulation. Everything is extremely expensive, and finally when you have the results done, when the results are simulated, then the post-processing comes, and it's extremely important because when you do something wrong at this last final step, everything what has been done before is ruined and wrong. So even if you do everything perfect and you do poor post-processing, everything is poor. So extremely important final critical step. Visualization is one part of post-processing, right? To make it visual, to visualize the fields and everything is one big thing. It's a huge strength compared to, for example, measurements. Typically, physical measurements are measuring something in single point or points with some probes, and the information is incomplete. There are, of course, other benefits of measurements compared to engineering simulations, but definitely a big advantage of the engineering simulations is having the whole information about all quantities, all basic quantities everywhere in the simulation domain. It's a huge advantage. So visualization is really part of post-processing and really important. But of course, the images does not mean we have an understanding. There's a huge difference between the visualization and the interpretation of the results, right? So we can visualize them, and if we visualize them correctly, we have to learn to read them, to understand them, to interpret them well, and that's the value we can be. Then we can get the value out of it. So that's important to realize the difference between, okay, we made something visual, but where's the value for us, right? What's the lesson to be taken? That's really important. We use ParaView. That's definitely for we think it's really great tool, which is it's open source. It's really great tool that helps visualizing the fields, the quantities in space. That's really great, and not only this, but even in fact so much more. So there are, sometimes I say there are endless visualization possibilities. You can take a look. For example, I guess you did, but still you can take a look on, let me see, on our website. Anything what you can see on our website has been created in ParaView. So all the visualizations were created in ParaView. Also, I would recommend to take a look on our YouTube channel where we upload quite a lot of stuff. Again, almost everything was created in ParaView. Maybe maybe you can take a look on our Instagram or something. But anything what you can find there, that's my point, has been created in ParaView. So ParaView is extremely strong and free tool for engineering data visualization, and that's why we like it. It's when we talk about post-processing, it's important to understand the kind of data, right? The data details, what we are looking at, what are the sorts and the groups of data, what we are what we are observing. So I guess you know that there are scalars, scalar fields, there are vectors, there are derived quantities. So there are there are some basic quantities which we simulate, and that are the real results of the simulation. And then there are derived quantities. There are so the volume fields, they live in the volumes, right, in the space. There are surface fields that they live on surfaces, which are typically flow rates or fluxes, for example. So that's the group of visualization, right? To see it, it's sometimes really important. And one big group of post-processing quantities is integral values, right? It's again a valuable contribution of engineering simulations, that the one big group of results is integral values, right? So that they are stored somewhere in CSV files, in some tables, that where you can see those various averages, various quantities that define the whole state, right? So those are numbers again, but really representative numbers what we wish to see. So for example, torques or some forces. So I would say in every CFD project there are some forces, right? You always look for some forces in various forms, of course, but integral values are extremely important. Uh, as mentioned in previous webinars, again, everything is about goals. Your goals are something which is incredibly important, because the goals, they define everything. They define success, they define what's good, what's bad, what they tell you what you are looking for. So always, and of course as well in post-processing, you look for your goals. Every project, every simulation, every engineering simulation has its nature, right? Sometimes it's research, and in research you often look for the existence of the solution and for the visualization, for example, while in the standard tests you have run million times in the past, and you just run it, you just use it as a calculator. Yeah. So then you're more likely looking for integral results, right? So it's always about goals. That's definitely my point. For a little while I'll switch to ParaView, or I mean, this is TCAE, which is our software where you can set up the simulation, you can run it here, follow the convergence, and evaluate the results. So pretty much everything you have to create the geometry somewhere else, but the rest of everything can be done here in ParaView, in TCAE, which is its home is made of ParaView. So yep. So I have a simple tutorial, which is our tutorial of Kaplan turbine. And what I would mention here, those are really, I would say, just the basics, right? Sometimes it's difficult to start with ParaView. So I'll only mention a couple of basics that maybe what's for me very important is the views, right? So every time you open a new view, which is called layout, or you can rename it, of course, but by default it's called layout. You open the views, right? And you can say what kind of data representation you would like to see. So often we have this 3D CFD connected with 3D geometry. So for that, there's definitely the render view, which is the basic view in ParaView. I personally quite like this item view. Maybe I will try to open this one. and in it I can start visualizing the geometry. So there are a lot of options for these views. I would like to okay, I will go ahead with what is offered in ParaView. So these views are extremely important. You can of course have HTML view, you can have line chart view, you can have plot matrix view, you can have really spreadsheet views, you can see the tables, you can see pretty much anything, and you can create your views. So it's definitely very flexible, and yeah, it's open source anyway. So yeah, so the views, right? There are a lot of views, and yes, also the line chart view can be this, right? You can follow the residuals, or you can follow the efficiency, right? So that's the line chart view, for example, or you can watch some statistics in HTML view, right? So there are views, and these views they are like basic interpretation of the data. It can be 2D, 3D, or spreadsheets or whatever. Then I would like to mention that there are sources. You can with sources you can actually create things. So you can add I would say individual components to your data visualization. So sources. Then there are filters. There are a lot of filters you can use. So you can really play with them. There are a lot of filters. Some of them are very often used. Some of them are always used. Some of them are rarely used. But there are a lot of filters which you can apply on your data, and you can play with your data. I would like to definitely mention that the basic filters which are typically on your panel with these shortcuts, the calculator, contour, of course, clipping, slicing, thresholding. You can extract data. You can use vectors, glyphs. You can use stream tracer to follow the paths, and there are a lot of really interesting filters. I'll go ahead that there's also geometry representation where you can follow, for example, the plane surface, or you can follow view it with for example, you can view the mesh with the edges, or you can see obtain various other representations in points or in edges, etc., etc. So that it's this. And the next what I would like to talk about is you have different panels which are really important too, because in your pipeline where you have your items, that's the pipeline browser, you have your items there, and each of these items have each of them has its properties. Extremely important panel where you can set everything, its definition. You have panel view where you can see set the, I would say, the colors. In the display panel, again very important. You can follow various forms of again the data representation. So I can maybe quickly click here that I like this call front face, back face representation in back face styling in the display panel where it helps me to look inside, because it basically it hides the it hides the front faces of the object, so you can look with it inside the object, for example. But it's just an example. There are a lot of visualizations everywhere. So these panels are extremely important. Display also information tells you, for example, the size. So this one is huge. It has something like 50 meters in X direction, and last but not least, but the last one is multi-block inspector. Again, very, very important guy, because you can split your model with it into pieces, and you can very easily look at what you want to look at. So these are panels. And what else? There is endless possibilities what you can display. Maybe if you would like to ask about anything, you can help us. You can create such videos like this, for example, in ParaView, because you can open multiple views. You can add multiple text options and the colors and everything. So ParaView is really really complex. And here I would maybe hand over the presentation to Radek. I will only finish with the last point I would like to make, is that almost anything is possible. You have to know your goals, definitely. And the last point I would like to mention is it's all about the experience, right? If you're first time in ParaView, it sometimes may look difficult, because there are a lot of options that are not directly, I would say, clear from the beginning. So sometimes it takes some time, but when you learn it, you will be totally happy with ParaView, because it offers a really, really complex and detailed post-processing options. So yeah, I will hand over the presentation to Radek. I hope I will find where to do that. Let me see. Yeah. So yeah, no. Where do I do that? Radek, here. Make presenter. Yes, here. Yeah. So we've got it. So Radek, can you? Are you
Okay.
following?
Yes, I'm carefully
We,
following.
we can see your screen,
And
Radek.
okay, perfect. Great. So thank you, Luboš, for the introduction and general tools which we can find in ParaView. And I will smoothly continue. So first I will quickly introduce the post-processing tools, or to check the results we have directly from the TCA simulation, mainly the integral values. I typically say that the integral values which are automatically processed and averaged and integrated are the can be understood as the general properties of the case. Yes, with efficiency, torque, pressure difference, etc. And then the visualization is to interpret the local properties. So you can zoom, you can visualize any quantity you need, pressure distribution on the blades, or flow separation around the blades, yeah, to visualize streamlines, visualize glyphs, etc. And also one of the most important part is to have a nice visualization of the results to present to your bosses, to other departments, to have a nice and overall view on your case, on your project. So first of all, let me start with the with the TCAE and the direct output to be post-processed and to be, let's say, to read and understand. So first type of the output is the HTML report, which summarizes all the results and all the case you have just simulated. So the report includes the standard information. I will be very quick because I think we have mentioned it several times during our previous webinars. So you have the simulation statistics, you have the basic, let's say, view on the convergence. So anytime you see something weird graphs which are not which are oscillating heavily or not going down, but mainly going up. So I think you will directly see if the results are meaningful here, or if something very wrong happens during the simulation, like the simulation diverges or any other stuff. So this is the first view, which tells you, okay, if the simulation is okay or not. Yeah, you can go for analyze if, for example, your y plus goals and other parameters are okay. Then there are several these integral values like the head, efficiency, and others. You can always follow the final results. It means the results at the end for each simulation point or simulated points. For each efficiency, you also see the convergence, which is the blue line. The red one is the averaged value. So you can also check if all the quantities converged well. Typically, if the average value reached the constant state. So this basically holds for any any part of the or for any section in the report. So you can carefully follow all the quantities and for example create your first impression, the first analysis of the results, compare it with previous measurements or previous results, and basically this is the most important part, I guess, because this is what at the end what you need to have, the parameters of your machine in terms of efficiency or local properties like the power, torque, or pressure at a given part of the domain. So this is, let's say, the summary of all the integral quantities that are evaluated automatically out of your simulation. So this is the first. If you need any advanced post-processing, or if you need to evaluate any specific formula for, so for example, if you don't want to evaluate, for example, total efficiency, and you would like to evaluate from the static pressure, for example, not from the total pressure, then you can go into the project folder on the disk. So this is, we have it here. And then if you go to the simulation run, into the TCFD, and you can find all the quantities which you find and many other quantities which you find in the report in the CSV files. So for example, if I go, as I said, into the TCFD folder, into the post-processing, sorry, not post-processing, but to the stationary or transient, if you are simulating transient case, then here in the stationary, you go for post-processing. Then here you have several folders which stores the integral values. So let's start, for example, with the efficiency, which includes the most information about the results. And here always we have a couple of files. First is the efficiency, which stores all the information for all time steps or iterations. So you can also plot your own convergence graphs for all the quantities, but mainly we are interested in the final values. So anytime you just double click and you can open it in your spreadsheet view, so in Excel or LibreOffice, and you can find all the quantities, and you can quickly create the plots or define your formulas to evaluate specific quantities based on this. So you have total static pressures, you have you have the differences, you have the pressure ratios, you have the magnitude, velocity magnitude, and other quantities on the defined inlet and outlet from which the efficiency probe was evaluated. So this depends on the topology of your case. So if I go back just to see the topology, so for example, here we have this Kaplan turbine, this tutorial turbine, and it consists of, if I count properly, of 5 components. And on any interface, so on both sides of the components, on the inlet and on the outlet side, we have also the integral values automatically evaluated, and you can find them here. And so each of this folder refers to the interface on the given component. So if I would like to see what are the values, for example, at the outlet from the stator part, from the green one. So I think we call it stator. So we have these two, stator from inlet extension. So this is this interface, and we have here stator to rotor, which is the outlet interface. So if you go in, then we have again a couple of files, and in the interface is final. Now we have the quantities, the integral quantities of total pressure, static pressure, flow rate, velocity magnitude, and the circumferential and meridional angle, if it makes sense to evaluate. So again, here you have the pressures and all the quantities, which again you can read, you can copy out into new spreadsheet folder with combination with any other interface, evaluate your specific pressure differences or whatever, and again to process some quantity which is important to evaluate for you to analyze the case. Yeah, so this is basically all the integral values which are very important for CFD engineers, because these values basically define the performance and the main flow parameters of your simulation. So these are the integral values. And then if you would like to go to study the local properties of the flow, or evaluate visualizations, and for example compare some specific part of your simulated domain or of your machine with previously simulated case, with for example, if you are studying and for example optimizing the shape of the blades or any part of your domain, then you can visually compare what are the differences of pressure distribution, or for example the flow separations at the given parts. Then you can nicely go for the loading the results and visualize the results. So you have two ways how to visualize the results, as Lubos already shown us. First one, directly from the TCE project. You can click here, you can create a new layout with the render view, and you can click here, you click here, display the results, and then choose what part of the domain and which quantities you would like to see and be able to list in the render view, and consequently also visualize. So this is the first one. But whenever you are just, let's say, playing with the visualizations and you don't want to play with the project itself, so you can anytime go on your disk, open new TCE session and load just the results, which can be quickly done. For example, just going into the case, into the given type of the simulation. So again, here stationary, and you can open this tcfd result.foam, and automatically the results are loaded into the ParaView and can be processed and visualized by standard ParaView visualization tools. Okay, so let's do it. Okay, so I will load it just to see the flow domain and the results in my render view. Okay, make it full screen, and let's go for it. So first of all, ParaView offers you to combine any results or any object with any other object. You can fill the pipeline with the sources, filters. You can apply the filters on any item for which the filter can be applied, and to save the memory, because for example, I would like to combine the visualization of some slices of the volume mesh and to this I would like to add just the surfaces of the blades, for example. Yeah, to combine, to see the blade surfaces together with the slice, etc. And so one option is to visualize, for example, just the hub of the rotor. So you can list or just the rotor surfaces, including the blades and hub. So I will uncheck the internal mesh. So now you can see I have just the surface of the rotor. But to this I would like to also add the slice somewhere through the volumetric mesh, through the volume, right? So one option is to open the new foam file to load the data, but this time in the memory I have loaded the results twice. So from the memory point of view, it's not the best approach. So what I can do is to, for example, I will load all the items and of course all the arrays, all the fields which were evaluated. So I will load all of them to load all the data I have available. And then there is a filter which is called extract block. Yes, it's this one. And I think there is also the icon somewhere if I'm right. Okay, I don't see it here. Yeah, it's here. So this one, extract block. So you can click on this icon. And first, okay, I would like to have one item for application of the slices and all the filters for on which I need to apply on volumetric mesh. So I will check just the internal mesh. Okay, so this will be first extraction, right? And I name it, for example, volume. And I will do the second extraction just to see, for example, the surfaces of the stator, blade, and the hub, for example. So I check only the stator shaft, for example. I will skip the shroud because I would like to see the inside and I don't want to block my view by the shroud. And the same I will do for the rotor. And I think there is also the hub which goes to the outlet component. So let me click these parts. I will name it surfaces, for example. Okay, without misprint, surfaces. And now if I visualize just the surfaces, I have a nice view on the surface. And what I can do now is, for example, I would like to see a slice just to visualize, for example, the contours or the streamlines on a slice going somewhere in the middle between hub and shroud, for example. So I can create a volumetric sorry, I can create slice. So as you see, first you need to click on the item on which you would like to apply a filter. Then you click. So this right now I would like to apply slice. And here in this properties panel, you can adjust the slice properties. So for example, now I would like to do the cylindrical slice, which is aligned with the z-axis, which is my rotation axis. I will align to the center, to the point 0, and the radius I will decrease to the radius of my hub or shroud. So I will put somewhere in the middle. So now radius 0.055. Now I can click apply. Sometimes it will throw you this warning about splitting the VTK polyhedron function, which somehow split some weird shape cell, for example, but it doesn't affect the view, but sometimes it will throw the error, so you can just ignore it. So I will click here to disappear the slice selection, and now I can, for example, visualize the velocity contour. And for example, what I would like to see is the relative velocity on the rotor side. And now, for example, now I would like to apply the surface LIC filter, which will nicely visualize the surfaces. But because my domain is pretty long, I would like to cut it. So on this slice, I can apply the clip. I would like to clip it by the plane which is perpendicular to the Z direction, and I will move somewhere here. And now I will click apply. Right, so this was the other half. So I can click here, invert the clipping plane. I can disappear the show plane, and this is my slice, for example. And now I can visualize, for example, a surface LIC. Yeah, it takes some time on this computer. I don't know, maybe because the graphics is not so powerful. So now it computes the LIC filter, which is the, I don't know the abbreviation, but basically it will visualize the streamlines on the surface, as you can see. And then you can play with the visualizations. For example, you can color it not by pressure but by velocity, etc. But it really takes a long time on this computer. So this is one quick representation of the LIC filter. But for example, as you can see, the streamlines look weird. So I think it's because it's evaluated based on the absolute velocity and not relative velocity. So if my computer goes quicker, you can click on the display, and in the display section, yeah, here perfect, there is a section for definition of LIC properties filter, and here you can switch to the relative velocity, and now the relative velocity is automatically evaluated, and in the rotating component it automatically evaluates the relative velocity. So what you will see is that in the stator parts the streamlines remain the same, but for the rotating part the streamline will follow the blades lines or whatever. So like you are sitting on the blade and looking on the flow. Yeah, so as you can see. All right, so this is the first visualization and basically the combination. I will get rid of this LIC filter because it really slows down my computer. So let me uncheck the surface LIC filter and go for simple surface visualization. And maybe then let's go for additional filters to show you. All right, so this was the clipping. You can see you can combine with every, for example, wireframe, and really you can combine with other filters. So let's go for it. So for example, what we can do is to create what I like, maybe if I see the nice surface, is to create a pressure contours. For example, it's a nice visualization. So first of all, what we have here is the pressure in kinematic pressure. So which is the pressure of which is the default mode in for incompressible cases. So the pressure is the relative pressure divided by the density, so so-called kinematic pressure. So for example, to see it in the real pascals, so you can apply the calculator. So on the surfaces, yeah, exactly. So I would like to apply on the surfaces. So I will apply the calculator, and the calculator works in a simple way like the other calculator. So first you will define the name of the new field. So I can call it pressure instead of just P, and the pressure will be calculated from the available scalars or vectors, but I would like to compute it from the static pressure. So to to transform it to the pressure in Pascal, I need to multiply it by the density. So it was density of water which we set. So it was 998 kilograms per cubic meter, of course, and then we would like to add the reference pressure which we set, and the reference pressure was simply the atmospheric pressure. So I'll calculate this. All right, now we have, as you can see, the new pressure values. So it's here, and I can scale it to reasonable values. So there is some Okay. All right, I'm fine. So, okay, I will focus the best way to focus somewhere and use this eye view. All right. So, but still the values looks weird. So I'm not sure what was the original values for the pressure. Okay, but never mind. Maybe I will just put wrong values which do not follow my setup of this case. But in this way, you can transform the pressure in the pascals, or you can play with any transformation of your quantities to the new one. So I will let's go back to the pressure, for example. So now what you can do is for creating contours. So first I will rescale my view to some range I would like to see. So for example, I don't want to see just the minimum pressures of this. I would like to see nice, let's say, contours and the region. So let me, for example, try this one. And to keep the scaling you set here, you just need to uncheck this enable automatic rescaling. Because if you for example, go for the next point, it will automatically rescale the quantity. So I don't want it. So I would like to keep the values in this range, right? So for example, okay, this looks nice. And to create the contours, what I can do is first going here into the color palette browser or panel, which can be enabled here by this edit color map, right? Also color map editor. So if I get rid of it, so you will enable it again by this icon. And here is the number of table values. So for example, I would like to see just 20 values. And always here you have two variants of value representation. The first one is with this box, which shows you the value in the cell or on the face, as you can see. So if I add the surface with edges, you can see the constant value for each face, while the pressure with this point is interpolation to the vertices of cells or of faces. So if I switch to this P, you can see nicely smooth, more more convenient for contour visualization. So I will keep it this. And for example, to enhance the boundaries of each contour or of each constant section of the pressure, you can create the contours on it. So I will apply on this calculator. Uh, you can apply the contours, and now you need to set a specific range. So the specific range needs to follow your legenda or your ranges of the given quantity. So you can set, for example, not for example, but in this case, minus 500 and 300. And because we have chosen 20 contours, so 20 sections, so we would like to follow the edges, we need to have 21 contours. So I will apply 21, and after applying it, it will create the contours, but not of the pressure, but of the static pressure, right? Perfect. Maybe I will color it with a native with a constant color, and I will enable visualization of my pressure distribution. And for example, the contour, I think the color black will be much better. Perfect. And now you can see now nice pressure contours with the boundary enhancement. And again, for example, now I would like to make these contours thicker, so I can go to the display, and here line width, I can set larger number for line width. So now we have nice pressure distribution and the counter visualization. Yeah, that's perfect. And for example, to visualize also the flow into it, we can visualize the streamlines, the volumetric streamlines. So this can be evaluated pretty easily. So I will click on the volume because streamlines, I would like to visualize the streamline not on the surface, but in the volume. So here I will click on the volume, so the extraction of the internal mesh, and now I can apply the filter streamlines, which is this one, so stream tracer. And if you go to the properties, you define the stream tracer. So stream tracer or streamlines are defined based on some random seed of the points from which the streamlines are evaluated. You have two options. First, to create a source by the line. So for example, if I place, sorry, so I need to place this line into my volume. So for example, I will visualize also the volume. Here you can click display just to see only the contours, for example, or not contours, but to see the domain boundaries. And the streamline tracer needs to be placed somewhere, so somewhere where it cuts your volume. So for example, just by an example quickly, so put it somewhere inside, and this line will create the seeds for defining the streamlines. So there are additional properties. So line is here, and resolution means how many points are generated on the line. So let's start with 500. And for the other options, okay, I would like to apply on the velocity vector, and okay, I will keep it in default just to quickly see. So first, you see that it creates the random points on the line, and through these points, which are placed within the volume, it will create the streamlines. What you can see that on the interfaces, it disappears. The streamline disappears. So we can switch here the interpolator type not by point locator but by cell locator, which will improve the streamlines going through the interfaces. So basically, the stream paths are not evaluated based on the interpolation to the vertices of the cells, but it sticks within the cell centers where the value of velocity sits. So it much better follows and follows the interfaces and go through the interfaces. So this is the first option. The second option is, instead of line, you can use point cloud, which means that you define the sphere. So it works in a similar way. So you create this random seed by the volume of this sphere. So you will again put somewhere into your domain. So I will start with in the inlet pipe. You need to decrease, for example, the radius, right? Yeah. So as an example, it will be fine. Again, click apply. So now it will create the random seed of points within the sphere, and from these points, the streamlines are visualized. Right. So this is, let's say, the simple way of streamlines generation, but there are of course some advanced options. So I would like to show you. So for now, I will disappear my streamline generation, and for example, now I would like to have a nice streamline which goes through the, for example, stator. So what I can do is that based on the volume, I can create a slice. So let me show you. I will create a slice which go through the stator, for example, here. Sorry, I will zoom. Okay, so somewhere here, all right. So now I have a slice, if we can see it. Yeah, maybe I will move it a little bit further from the interface. Okay, apply. All right, this is fine. And basically, this slice is also can be interpreted by the set of points, and also these points can be used as a source for streamline generation. And for example, there are many points. Basically, it corresponds to some intersection of the cells and the boundaries of the cells and the vertices of this intersection. And just to, for example, make this raster more coarser, you can use another filter which is called, I think, mask points or something like that. Yeah, mask points. And here you can see the mask ratio. It means how the coarsening of the points which are available there. And you can choose, for example, the random sampling. And if I click apply, I don't know if it will be visible. I need to go back to the points and generate vertices. Sorry, I need to generate the vertices. So this is my new, let's say, point cloud, and this was the original one. So you can see we get rid of every second point maybe. So if I increase this ratio number, so I can make it even more coarser. And now I can use these points to create a streamlines. So for these options, there is a filter which is not streamlined but streamlined stream tracer with custom source. So we can apply it. Now the input is the volume, because I would like to generate the streamlines in the volume, and the seed source are my mask or the slice, but I would like to apply on the mask to get the the seed points more coarser. So let's apply it on it. And now if I apply this filter, so now it computes the streamlines which goes through all these points. And maybe still there are many points, and after it we will see nice streamlines going and be more equidistantly distributed through the sections we have chosen. So in this way you can more sophisticated, or in a more sophisticated way, you can create the streamlines for your cool visualizations. Yeah, perfect. So this is what we have. So nice streamlines, and maybe I will switch back to the cell locator, and to have a nice streamlines also on the rotor section, I will switch to the relative velocity. And now we will have a nice visualization of the streamlines together with the pressure contours in our tutorial Kaplan turbine geometry. And basically, in this way, you can combine any visualization with any other filter like glyphs or any other, basically. So what are the main output of this example is that you don't need to load the results anytime you need to evaluate or visualize new part of the geometry. So do it just once. Load all the parts which you will need for the visualization, and then extract each part by the extract block, on which you can then apply either, for example, a streamline tracer, or just for visualization the surfaces and for example the pressure distribution. Okay, so streamlines are loaded, and now, for example, you can play with the visualization of the streamlines. So we can go to the display, and we can color it not by the pressure, but for example by the absolute velocity. Okay, for each you will have the legenda, but you can get rid of the legenda if you need. And I will just scale the velocity, I think up 30, for example. Okay, looks nice. Now what we can do is to add the line width to be more thicker. So as you can see. And what I also like is this visualization option to render the lines as tubes, which gives the view more plastic view of the streamlines. And what is also cool is to apply the opacity on the streamlines. So if I have enabled the streamline tracer here, and I can click here enable opacity mapping for surfaces, and you have nice visualization. Yeah, of course you can change the opacity by adjusting this graph, opacity graph. You can change the range of the for the velocity or pressure to combine to achieve your favorite visualization, etc. Oh, and of course you can choose the different representation of the coloring, so you can apply any other favorite palette or preset colors. So let's go for example this one as an example. All right, so this was the example of combining any filter with in combination with any other filter. All right, so I hope if you have any question what to visualize more, so please put it into the into your question section in the webinar application. And maybe now I can show you some additional visualizations, maybe a little bit advanced, but I think still clear. Okay, what I didn't mention, I can show it right now. So this is my, let's say, preset view. I would like to keep, for example, for other results, for other visualizations. So what you can do is to go to the file, to click save state, and save the state into the file. So for example, my state, or yeah, let's keep it my state. And anytime you would like to reproduce the same visualization and maybe on other results. So typically you run a little bit different simulation with, for example, adjusted geometry. So you can open the paraview again. So I will open the plane paraview. And then, okay, it's already here. Okay. Now I don't want to play with the manager, with the TCA project, so I can delete it, and I can click here just to load state option, locate my my saved state, and here if you like to use the same results, you can keep it as it is, or if you would like to switch to another result of the same topology geometry, of course, then you can locate it and click on the given form file. Okay, and the same visualization should be loaded, and you will see basically the state where you save it. So this is good to keep track with what you have visualized. And for example, sometimes if you put a lot of filters, maybe sometimes it's memory hungry, so it can crash the paraview because of memory leakages, for example, or basically because your all memory runs out. So then it's good to time save the state to keep your working backup. All right. Okay, so now it loads our visualization we have done. Yes, perfect, it's back. So you can see that it nicely works. And for example, what I would like to show you next is some additional example of a little bit different topologies. So here I have run some transient simulation of the external aerodynamics, very simple case. So let me open it. And let's show what we can do, for example, in terms of visualization of turbulence, which is pretty demanded visualization for external aerodynamics, but not only for external aero, but also for internal, if you would like to really see. And if you have the transient simulation with DS, turbulence modeling, or LES, but I think it's not even not possible with regular resources. But with DS, you can run a nice transient simulations where you would like to focus on the turbulence and, for example, visualization this cool wakes behind your object or whatever. So let's load it in the same way. So again, I will load all the parts. I will load all the quantities, and let me quickly show the basic visualization. Okay, so this is a simple virtual tunnel or arrow tunnel with the obstacle in it. It's a simple cube, and we have simulated in the standard way. So we have, I think, something like 20 meters per second at the inlet. Maybe I can show you the slice, what is happening inside. Okay, I can show you the velocity, and I have simulated 2 seconds. So if I go on back at the end of the simulation, so you will see some nice turbulences behind the obstacle. And now what I would like to do is to somehow visualize the turbulence. As you already mentioned, but I haven't opened it. In TCA, you can ask for evaluating vorticity or Q criterion, which is one of the main main fields for visualizing turbulence. So what we can do is basically we have the volume and we have these fields. So we can evaluate or visualize the Q criterion and vorticity. So let's visualize both of them. So for again, because I would like to combine the volumetric data and apply some filters on it, and also to visualize the obstacle itself. So again, I will split it into parts. So first I will create just the internal extract block, and additionally I will do also the, for example, minimum wall. So this is the bottom of the virtual tunnel, and the obstacle itself, which is this part. Right, so perfect. So this is my geometry and this is my volume. So if I apply the contour on the volume, I think this is the best way for visualizing the turbulence. And first I will apply on Q criterion, for example, and let's try value 10. So this will create the isosurfaces of the quantity Q with the value 10. So you can see nice turbulence eddies visualized by this by by the quantity Q. On the surface, I can keep it, for example, as a simple color, for example, with white. And what I can do with the contour is create display, click display, and decrease the opacity just to see more what is happening also in the middle of the domain, etc. Okay, to this, for example, I would like to add the same visualization, but not for Q, but for vorticity. So I can split the domain, click render view, and for example, I would like to focus, or first what I will show you, I will create the same visualization. So first, this second extract block, perfect, with the solid color, with the white, and to this I will add the contour, but for the vorticity, if I have it, okay, good. Now, because I have the vorticity, sorry, where? No, extra box, sorry. Yeah, I need to visualize it, and then I have here only the vorticity, which is the vector, but the contour can be applied only on scalar. So first I need to compute the magnitude of vorticity if it's not already computed. So I will create new array name, magnitude vorticity, for example, this way, and then I can apply the magnitude on the vector field vorticity. So it will calculate the magnitude of vorticity, and now on this I can apply, I can use this mag vorticity to create contours, and I don't know, again I will try to put the value 10, and perfect, and this is the contour of vorticity. And now, because I would like to have the same view, I can right click on one of the render layout. I can click here link camera and click to which render view I would like to link cameras. Okay, and now if I am changing the camera position, it's changing for both views. So in this way, we have the pressure contours, pressure vorticity contours, and what we can do now, of course, play with the visualization again, changing the opacity, for example, to the same level as for the previous one. For example, we can switch to different color, okay, to distinguish these two quantities. What you can also do is to, for example, add the current time to be visualized and later to be viewed in the animation. So you can click annotate time filter here. Perfect. Now I can see the time, and for example, you can also add a filter or the source, as Lubos mentioned already, and you can add a simple text, and for example, name it as Q criterion, but not in this way. So we need to go up. So here it is Q. In the display, we can put it on the right corner, for example. And similarly here, we can create a new source with the text and, for example, name it as vorticity. Okay, or magnitude to be more precise. Perfect. And now, if you change the time frame, of course, the particular data will be loaded. And to create the animation from it, you can go here to File, Save Animation, create the name of the animation, test animation, for example. Okay, here you adjust the parameters. So I would like to save all views, so all render views. Here you preset the image resolution, and then you will hit OK, and all the animation, maybe I can do it, and all the time frames will be stored as images. So now if I go back to my case, so let's check if I'm in the correct one. Yeah, I think it is. Yeah, test animation, and now you can see the images are rendered. So I will go back, and basically what you can do. Okay, I would like to stop it. Yeah. So, and what you can do. So if you adjust your view, etc., you can then have the animation something like this, in which I have compared, for example, these are the way we have done with different views. So for example, here we have the Q criterion with different values. Here we have the vorticity magnitude with different values, and you can nicely compare it. Basically, if you have two cases, so you can combine in the similar way the results from two different cases. So which I made, I think, here. So this is the visualization of the case with turbulence at the inlet. I don't know if this one, yeah. So this is the same, but with some artificial or random turbulence at the inlet, and at the end with some base scripting, but maybe it's not the purpose of this of today's webinar. But at the end, what you can have, I don't know if it will be properly visible, to have the animation of comparing all these visualization within a single window. So all of this can be done, and as you can see, there are almost unlimited way how to do the visualizations. And maybe what I would like to add, I have two more things maybe to show you. The first one, okay, what I didn't mention it. Okay, so all of these are connected with the visualizing the results, but also with ParaView you can also post-process the integral values. Yeah, so for example, you can simply compute the flow rate in any section of your domain you need. So just to show you quickly this, because time goes by pretty quickly. So let me, for example, open the Kaplan results again. And what I would like to show you are maybe two things in one shot. All right. So first of all, the ParaView also provides to script all the visualization, so you don't need to click anytime. You can create a script which you can run then automatically or from the console to create all the stuff you have defined, or when you are more familiar with the Python code, because the interface behind it is so-called ParaView Python, in which you can script all what we have basically done by clicking. And there is a nice tool which is called the tracing. So you can record everything you click, and it will be stored in the Python script, which can be loaded back or run in the console to do the same steps you done in the graphical user interface, or even you can modify it and create the visualization or any other evaluation automatically. So I will click here start trace just to show you how it works. And basically here you can choose which properties will be stored, if any property which will be touched by your click, or just the user defined or the property which will be affected by the clicking, or all of them. And here you can also add a show incremental trace. So anytime you change some property, it will show you the code which basically do these changes. So this is really nice for learning the ParaView Python interface and how it works. So I will keep this one. And now let's open one of your results. So I will open these Kaplan tutorial results. And as you can see, right after opening, you will see the code which needs to be done. And you have several lines which basically loads the results and load them into the scene we have here. So what I would like to show you is, for example, how to visualize or how to evaluate the flow rate at any intersection we have. So for example, we don't have available the flow rates, for example, for TCA or whatever, or I would like to, for example, evaluate the integral values of the static pressure somewhere. So you can do it in this way. So I will create a general slice. So as an example, for example, I would like to see what is happening somewhere here in the elbow. So I will click apply. Perfect. So I have this section, and now I would like to know what is the flow rate here, for example. So I can apply the filter, which is called surface flow, I think. Yeah, here, surface flow. You can define the field from which this surface flow is evaluated. So it basically computes uh, for each face on the intersection. It computes the normal component. It computes the surface area of that face and the normal component of the velocity, and it multiplies it and basically integrate it. So by now we have evaluated, but the results are not in the data sense, but in the, let's say, just the values. And to visualize these values, you can open the spreadsheet view here, visualize the surface flow, which was done automatically, and now you can read the surface flow, so in SI units. So this is a cubic meters per second. And for example, you can adjust it. So for example, I would like to see just the surface flow, and I would like to save it into the CSV file, so flow rate. Okay, you can adjust the precision, and now you can see that on my disk we have there is a flow rate value with my surface flow for surface flow value. And for example, right now I am satisfied with this, so I can store this Python script, so I can save it. I will put into my uh, into my working directory into the project case, and flow rate, I will name it as flow rate. Okay, and what I can do now, so if anytime you have stored, I will delete my flow rate. Or what we can do, for example, go what is happening inside. I don't want to go into much detail, but for example, here you have the file which is exporting the CSV, so you can rename it or put in any place. So my flow rate, for example, I can call it, click save, and now I can run the Python script directly from console. So I can run the command line. Now you need to locate the Paravi Python executable, which is within your TCE installation. So my current version is this one. There is a bin directory, and there is somewhere pv Python. Then, just as working with the standard Python, if you would like to run it with the script, you just add the option -t and the name of the script, so flow rate. You will run it, and whenever it does everything what was defined or what is defined in the Python script, it will put your flow rate out. So you have here surface flow, and in this way you can manage, you can modify the script. So for example, if I would like now to uh, output all the values for flow rate for all my results, so we can go, for example, for ParaView documentation. So if I type ParaView documentation, so on the first item here we have the ParaView user guide, and somewhere here, for example, in the animation, you will find how to work with animation data in the script. So we have some example. So if you would like to go to the next, for example, to the next slide, to the next result, which I am here, right? No, sorry. It was here. So basically, if you go for any other slide, to go for the next, to go for the flow rate of the next point or the chosen point, so you can find a command using which you can do it. Or if you would like to iterate over all of them, so there is these functions which will return all the times available or computed basically in our sense. So I can go on my disk. I can, for example, go for a flow rate, and I can create. So I can load my scene, but my scene calls animation scene, I guess. Yeah, animation scene 1. So we can take all the times, and then in the loop, what I can do, so for t in times, I can do all these export, and for example, I can just create the name of the file based on the time value, and just to update the scene, which is somewhere here. So anytime we go for the next time frame, there is the command something like update. So I think we can go it in this way. I hope it will work. No, sorry, animation skin is not is the spreadsheet view. So for going for the next time, we need to update the results. And the last one, I need to go to the given time. So I think we did it here. So if you would like to go to the given time, so there is this command. So I will just copy it out. I will go to my, which is here, I guess. Yes. So I will put this command, so animation scene, and go to time. Now T, update the spreadsheet view and export the spreadsheet view to given file. So let's keep fingers crossed. I will run it again. Okay, invalid syntax. So I did it something wrong. Okay, I forgot one plus sign. And I hope I did everything in the correct way. Something is happening. And now you can see, yeah, it is exporting all the files. So here you will have the results for the first simulated point, here for the third, and in this way you can done it. You can do the, yeah, for example, flow rate evaluation in the automated way. In the similar way, but in more steps, what you can do is to, okay, maybe I will stop the tracing. On the surface, sorry, on the slice, sorry, I'm too fast. Discard and stop the trace. Sorry, yeah. I don't need to record my trace anymore, but what I would like to show you is how to evaluate, for example, the static pressure average. So to do so, you can apply the integral variables or integrate variables, which is here. You can apply, and now the spreadsheet view is automatically visualized. And what I would like to do is to just go for the cell data, because I would like to have the area averaged value of the pressure or any quantity I have here. And basically this value is basically the sum of the pressure multiplied by the area for each face on the slice. What I mean is the basically surface with edges. So for all this section, so it multiplies the pressure value times the area, and this is the value. And to have the area averaged value of the pressure, you need to just divide the value of pressure by the area, or K, or any other quantity. And in this way, you can evaluate the area averaged, or even if you compute the flow. So, and you create a new variable, pressure times the local flow. So then you can also have, for example, the flow rate average values and at any slide. And with combination with Python scripting, you can do it in the automated way. So this was also the example of the scripting, which is a really nice and powerful tool for optimize the process. So if you have your project in which you need to have some special treatment in sense of evaluating something special, then you can click it in the Python, record it, do some modification with the script, and run it automatically after your simulation to get your advanced values automatically. And maybe still, I think I will take my last 5 minutes to show you the last thing what can be done in ParaView, last of many, but let me show you the last one. So what ParaView also offers is to, for example, combine two results and see, for example, differences of the pressure locally. So the difference of the pressure between two simulated cases. So for example, I will take this turbulence case. So if you load both of them, let me show you. So I will load the case without the turbulence at the inlet, let's say. So this one. And I would like to compare locally the magnitude of the velocity and the difference of the magnitude of the velocity for these two cases. This can be also done with ParaView, which is a nice advanced tool, which is not commonly known, but it's very, very nice. So what I will do is I will load both cases. So this is the case with no turbulence at the inlet, and this will be the case with the turbulence at the inlet. So turb in foam, yeah, this one. And now we can compare the pressure difference maybe everywhere. Let me check it. Oh, sorry. And okay. So what you can do is to create two variables to be compared with. So for example, let me compare the magnitude of the velocity. So I will name it velocity turb in, for example. I will define it as magnitude of the velocity. So this is my first field. Just to distinguish the name, because otherwise I will have two U fields, and the same for the other case. So for example, I name it in this way, velocity turbine. So velocity. Okay, I misspell it. Velocity turbine in this case. Sorry. And in this way, this is velocity no turbine, for example. Okay. And there is a filter which can combine both. Even you have non-conformal mesh, right? It's not the same mesh, but the same topology. You can create alphabetical, and this one is called resample with dataset. So it means it will take the source data from one case, so this calculator one, and will put on the destination mesh of the second case. And I would like to copy all the arrays which are available. So I think this could be it, I hope. But now I apply on the whole mesh, so I hope it will be done quickly. It seems that yes, I hope. Right. Now you have both values, so velocity for one case and velocity for the second case available on a single mesh or a single data. So what you can do now is to, for example, create a calculator, compute the field velocity difference, and take one, for example, velocity with no turbulence at the inlet, with the velocity with the turbulence at the inlet, and create the difference. And now you can visualize the difference of the velocities for these two cases, two different cases. So I will make a slice, for example, just to see just what is happening inside, and we can go to some later time, and you nicely see the difference, local difference between the velocity of one case and the second case. So this is nice tool for comparing, for example, the local pressure differences for two different cases where you, for example, just modified or optimized the blades and see the effect of this modification locally as a pressure difference or any other quantity difference, for example, velocity like here. So I think this is also a nice tool which ParaView offers, and there are many others. So do not be afraid of or looking for new filters and new options in ParaView, because there are many of them and which can be very handful and unique for you for visualizing what you need in your projects. All right, so I think from my side it's all what I would like to show you. Maybe I was a little bit more late than I expected, but I think we hadn't any deadline. So I think we can go back to Luboš if Luboš is still alive.
Yes, yes, Radek, absolutely. I'm alive and I'm excited about what you have shown. It's really great. So yeah, thank you, Radek, for your part of the presentation. Thank you very much. And yep, let's go ahead in the webinar. Let's go ahead because time is running very quickly. So yep, what has been shown, and let's continue. Yep, in here. While you were
Perfect.
talking, I was playing here with our TCE Lite tutorial formula here, but this is not exactly what I wanted to show because you have stolen me everything
Sorry.
what I wanted to show. So yeah, your contribution was really extensive, Radek. So I think we can move ahead in the presentation. So expert on air has been already done. Yeah, thank you for it again. And now it's time for questions and answers. And this is going to be really interesting because as far as I know, we have only one question here. Believe it or not, there are a lot of people here, but we have only one question. And but nice one, really nice one. And it says, what are the best practices for critically analyze the results? Which is not obvious, but the second question makes it more precise. Also, how to identify what is good result and what is a bad one. Yeah, good question. So I was thinking about it a little bit because the question is here for a while. And it's, well, honestly, if you run some project, some engineering simulation for the first time, then there's no chance to realize or how to find out if the results are correct or not. It's impossible because it's data, and the data can be correct, data can be wrong, and it's really difficult to make any assessment what's correct or what's wrong. What helps? I mean, we can only tell what helps. Definitely, what helps is the practice, the experience. So if you have run, for example, a case many times, then you will, I would say, develop your assessment. You develop your eye for good results, for bad results. If you have, of course, some measurement data you can compare with, then it's again so much. I would say the life of an engineer is easier than if you have some data from measurement to compare. And at the end, I would say the data has to make sense. If they make sense, then you are on a good way. If they don't, then there, then perhaps there's something that can be improved. So yep. So well, it's this, and I would like to ask the audience if you quickly can. Still, we have some little time to you can ask your questions, and we will do our best. Otherwise, we can conclude. Radek, what do you think?
Yeah, that this is a really interesting question, and it's pretty general one, right? So there are
Yeah,
several levels what you need to check, right? So
maybe
you
we
start
can
with
discuss this. Yeah,
yes, uh, you can start with what is the expectation and what are the physical values of the results. And as I shown at the beginning, you can start with the residuals convergence with the integral values if they fit the expected range of efficiencies, pressure, and power. And then okay, if it's in the expected range, then you need to go more inside, for example, to check the mesh quality for all the details. You need to check, for example, if some quantities are bounded or not, etc. So you need to go deeper and deeper if you need the analysis, if you would like to have the analysis in the sense of what is good and not good results. So sometimes if you do a benchmark and you would like to fit the measurement data, then you also need to think how the data was measured. So there are many unknowns and so many parameters that can
yeah,
influence the results that you need to go from the yeah, the most important one, so the general values. And if you would like to achieve the accuracy less than 1% with the measurement, then you need to check all the detail including the mesh quality, local mesh refinement, numerics, etc. So
yes.
yeah, so
Radek, this was a really good point. So we're engineers, right? So
mhm,
the things should make sense, right? So there
yes,
should be
definitely.
a lot of sense everywhere. But that cookbook you started was really good. So at first you have to be sure what you have set in the simulation, right? So
Mhm,
the simulation settings, it should be pretty I think clear and transparent to you. So there should not be like blind spots. I don't know what to set for this quantity, for this boundary condition. That would sound a little bit suspicious, right? But if you are certain about your boundary conditions, about your physical model, and simulation runs, and then it converges. So ideally the residuals should fall down. And
mhm,
if, for example, the everything is conserved, right? So if the
mhm,
flow rate or mass flow rate is conserved via a very interface, if the model losses are about uh, around the expectations, then you are on a really good way to have good results. And then you can check, for example, what's the effect of your turbulence model, what's the mesh. Of course, mesh is very important. And so it's always an iteration process, right? But yeah, so well,
yeah, and
it's
in this way you can go
individual.
into more and more detail here to check what needs to be checked to achieve the given accuracy. So
And also the devil is in the detail, Radek, right?
yeah,
We
yeah,
always
yeah,
say
yeah,
it in every
definitely.
project. Every
In every
project,
project.
but seriously, every project is
Mhm,
different. Every goals are different. Every budget in terms of effort, how much effort is going to be spent on the project is different, and etc. etc. So well. Let's get back to this. We
mhm.
really don't have any other questions, so I'll take it. Let's face it, let's conclude the webinar. So I would like to thank you. I would like to thank everyone for your attention. Still, you can come anytime back. We'll be happy to answer all your questions anytime, because it's our job and we have chosen it. It's our job and our pleasure. So let's come back anytime, and this could be it.
Yeah, thank you very much for your patience, right? And looking forward for the next webinars.
Absolutely. Thank you, everyone, and bye bye for now.
Bye bye.